Hello again, this is Coach Dorf. We're going to look at a problem from section 4.7 that deals with optimization problems. So here's the problem that we're given. We have a rectangular piece of cardboard, and the length here is 16 and the width here is 10. And what we want to do is we want to cut out corners that are in the shape of a square. So something like this. Take out these four corners, cut out those squares, and then we're going to fold cardboard along these dotted lines. And when we do that, we're going to get a box that looks like this. And we want to maximize the volume of the box there. So let me just give you an example. Suppose I were to take out the squares that would be here on the corners. If I were to say that these were 1 inch each. So we have 1 inch there, 1 inch there, and so forth. Then this length here that remains would be 8, so that the whole width now would be 10. And likewise, on the length here, I'm taking out 1 inch and 1 inch, so this would now be 14 inches, so that 1 plus 14 plus 1 would give me 16 for the total bottom length. And then when I folded that together along the dotted lines, I would get a box here that would have a height of 1, a base now here of 14 and for length, and a width here of 8. And so the volume of it would be 1 times 14 times 8, which 8 times 14 is 112. So that would give me 112 units. All right. But now if instead of taking 1 inch, if I took out 1.5 inches, it would give me a different volume. It would give me a different height. It would give me a different width, a different length. And if I took out 2 inches for each of the squares, it would give me a height of 2. I have a different volume, a different length for sorry, I'd have a different measurement for the length and a different measurement for the width, and so I'd have a different volume. And so the question is, what's the largest value you can take out, or what's the maximum value taking out X so that you get the largest volume? Okay, so what I want to do is how large the square be so that the resulting box has maximum volume. All right, so what I'm going to do is, again, in my rectangle here, I'm now going to call this length here X and this X. So I'm going to take out X, so it's going to be an unknown. Then I need to figure out what are the dimensions for the base of my box when I make the box. So originally, this thing here we saw was 16. So what is the now of the resulting part after I take out X and X? Well, it's going to be, this will then be 16 minus X, or 16 minus 2X. Likewise, the width here was originally 14. No, sorry, originally 10. And so now what is this width of the resulting box? Well, it's going to be 10 minus X, which is then going to be 10 minus 2X. So when I do it that way, the volume of the resulting box that I form is going to have a height of X. This length here is going to be 16 minus 2X, and this width here is going to be 10 minus 2X. So the volume is going to be height times length times width, which is going to be X times 16 minus 2X times 10 minus 2X. I can multiply these together to get polynomial. See, first I'm going to multiply the 16 minus 2X and the 10 minus 2X. It's going to give me 160 minus 32X minus 20X plus 4X squared. And now if I combine the negative 32X and the negative 20X, and then multiply everything by X, I'm going to end up with 160X minus 52X squared plus 4X cubed. And I'm just going to rewrite that in order with the largest degree first, so that I have 4X cubed minus 52X squared plus 160X. So that's going to be my function V. And what do we want to do with this now? So we want to find the max of V. And how can we do that? Well, we're going to use second derivative test. What's the second derivative test say? Second derivative test says first, I find critical numbers by taking the first derivative and setting it equal to 0. And then I'm going to use the critical numbers to find when the second derivative evaluated at a critical number is greater than 0 or less than 0. So I have to think about this for a second. If I want to find a max, so if I find a max, that means my function is going to look like this. There's a max. And using my second derivatives, that's a frowny face or a stormtrooper. So it means I have the negatives there. So when I have second derivative is negative, I have the frowny face, which gives me a max. So I want my second derivative to be less than 0 on this one. So that's going to be using the second derivative test. All right. So we go ahead with this now. We have x equals 4x cubed minus 52x squared plus 160x. I take the second derivative, or take the first derivative here to find the critical numbers. So I get 12x squared minus 104x plus 160. And I want to set that equal to 0. Whenever I factor here, I take out what's in common. They have a 4 in common. So I'm going to have 4, take out a 4, and then I have 3x squared minus 26x plus 140. And that's going to equal 0. Okay, let me just not write that part there. Okay. And then I'll break this up, do this. So I have a 3x squared. So that means one of these has to be a 3x and one has to be an x. My signs are a minus in the middle and a plus at the end. So that means that both of these have to be minus. And now I have to get two numbers that multiply to be 40. And when I put them in here, then the middle term is going to be negative 26. So let's see, 40, I can break that up into 8 times 5, or it can also be broken up into 10 times 4, 20 times 2, or 40 times 1. If I try putting numbers in here and looking at the middle term, I will see that the one that works is if I put 20 in here and 2 in here, then I get a plus 40 for the last part. That's going to be negative 20 times negative 2 is going to give me plus 40. So that's a check. And my middle term is going to be 3x times negative 2 plus and a negative 20 times x. And that's going to be a negative 6x minus 20x. That's going to give me minus 26x. Okay. So what I factored v prime to be, v prime of x is 3x minus 20 times x minus 2, and that equals 0. So that means then that 3x minus 20 equals 0, or x minus 2 equals 0. And if I solve for x, I get x is either 20 over 3 or x equals 2. Now, what are my possible values for how small can x be? Well, x is, remember, if we go back to the original problem, x is this. X is this length of the square that you cut out. So it cannot be less than 0. So the smallest x can be is, it has to be larger than 0. So x has to be larger than 0. It can't even equal 0. It wouldn't make sense because I wouldn't have a box then. It would just be still that cardboard if it were equal to 0. And if it were a negative number, that wouldn't make sense because I'd have a negative length. Also, large can x be? Well, if I just look at the polynomial, remember we had the polynomial that was back 4x cubed minus 52x squared plus 160x. Okay, this has domain negative infinity to infinity, but that is not the domain in this problem. And why not? Because we already know, because have the dimensions of a box. And we know, we showed earlier that x has to be greater than 0. And so what's the largest that x can be? So how large can x be? Well, could x go off to infinity? No, because then it wouldn't make sense with our box. So remember our box here looks like this. Here's our box, all right? So there's no problem with this part of x, but what about here and here, right? If x gets larger 8 in this case, then have a negative length here. So here we have to have 16 minus 2x has to be greater than 0. All right, so now if I bring the 2x to the other side, that means 16 is greater than 2x. Or then divide both sides by 2, I get x8 is greater than x, or you can write that as x is less than 8. Right? Likewise, if I take the other one, we have 10 minus 2x is greater than 0. If I do the same here, I'm going to get x is less than 5. So x can't be greater than 5, and it can't be greater than 8. So that means x has to be less than 5. So those, I need to keep those two restrictions in mind. X has to be between 0 and 5. Well, if we go back to our answers that we had up here, we had x, okay, critical numbers, x equals 20 over 3 and equals 2. Well, 20 over 3 is what? That's a little less than 7. It's 6 2/3. This is too large. Oops, that's too large. Because if x were that number, then remember then the width of our box would be a negative number. Remember, because we had this box here, this was x, right? And this was 16 minus 2x, and this was 10 minus 2x. If I put in, if x is 20 over 3, then 10 minus 2x is going to equal 10 minus 2 times 20 over 3, which is going to be 10 minus 40 over 3, which is going to be a negative number. And can't have a negative length. Okay, so it's not a possible answer, but x equals 2 is. So our only critical number, or the only valid critical number, is x equals 2. And we're doing the second derivative test. So again, remember, in the second derivative test, the first thing we do is find the critical numbers, and then we look at the second derivative at the critical numbers. So recall, first derivative was 12x squared minus 104x plus 160. So the second derivative is going to be 24x minus 104. And now if we look at the second derivative at 2, so this is my critical number, I'm going to get 224, which is 48, minus 104, which is negative 56, and that's less than 0. So what does that tell me? My second derivative is negative. So negative, stormtrooper, or frowny face, that means I have a max on my curve. Okay, here's my curve, and here's a max. So we have a max, x equals 2. So what does that mean in terms of this problem? That means that if I cut out a square of length 2 here in my cardboard piece and then fold it up into a box, I will get the maximum value. And again, if we look at that, so here's my cardboard piece. I'm now cutting out a part of 2 here, 2 here, 2 here, and 2 here. And so this length now is going to be 6 because the whole length was 10. And this length here is going to be 12 because the original whole length was 16. And so now I have a box like this, where this is 2, this is 12, and 6, and the volume here is going to be 2 times 12 times 6, which is 144. So the final answer is my x equals 2 is what I should cut out. All right, thanks.